Imagine being asked to develop one of the world's strongest materials in under an hour. It might seem like an insane idea that's, impossible, but in reality, all you really need is this. Let's dive into the world of graphene.
The key realization is that graphite, the stuff in pencils, is really just a bunch of layers of graphene stacked on top of each other. And what's more is they can actually be really easily extracted by using a piece of tape. As you can see, I just took a little bit of that graphite and put it on this tape. And then by folding it over on itself, I can actually get a bunch of smaller, lighter versions, which essentially is just graphene.
You might be asking yourself, well, why is graphene so special? And in reality, the whole idea is just that it acts just like a cargo net. It's really thin, flexible, and also has this grid-like pattern. And that's also what gives graphene its strength. In graphene, these carbon atoms are lined up really close to each other, so the force of attraction between those is also really strong. So that essentially makes graphene like this really tough to pull apart material, but it also allows it to bend really well because that layer is so thin that there's literally nothing to keep it rigid or straight. Likewise, it also means that electricity also flows really well through graphene. Because those carbon atoms are so close, the electrons on those carbon atoms don't really stay on one. They kind of flow in between all of them. And since electricity is literally the flow of electrons, it actually allows electricity to move in a way that almost reduces the loss of energy altogether. And while those all might seem like really niche properties, the reality of the situation is that all of these properties of graphene have the potential to impact everything that we do in our daily lives, ranging from architecture to computers to even the water that we drink. For example, the conductive properties of graphene actually make it a really good candidate for being a superconductor, or a material that allows electricity to flow with almost no energy loss while electricity is flowing. So it actually makes it a really big candidate for things like computers or even quantum computers, where energy conservation but also heat loss or heat release is actually a huge concern. The structure of graphene also provides really good filtering properties as well. Because of how close those carbon atoms are together and that little hexagon shape that it forms, it actually allows really, really small particles to pass through, but only the particles that you want. In some cases, graphene can be engineered to filter out specific small particles that could potentially contaminate water, thus leading to better drinking water. But the real question with graphene is, if it's such a no-brainer to use in almost everything, then why aren't we using it? Number one is the scaling cost. Right now we can only produce graphene in really small quantities, and even then, it takes a lot of money to produce. The resources, tools needed, and the actual effort required is a lot more than other materials we have right now. Number two is the quality control for graphene. Right now it takes a lot of highly specialized tools and a lot of resource-intensive processes in order to make graphene that's actually useful or actually practical. Without those tools, graphene actually becomes a lot less effective. There might be multiple layers not even being graphene anymore, or there might be missing carbon atoms, which just ruins the structural integrity altogether. Overall, the bottom line for graphene is really exciting. It has the potential to improve the standards of living for billions of people, and also improve the way that we do research and also gain knowledge with quantum computers. But the problem is, we just need more people working on it. We need more people who can be problem solvers and take on these harder problems. And I hope to be one of them.